lecture, I will start with probability of an event. The probability P of A of an event A from the finite sample space S is given by the ratio between the cardinality of A and the cardinality of S. So, it can be written in this way also: number of favorable outcomes for the event A divided by number of all possible outcomes. To find the probability of an event A, we sum all the probabilities assigned to the sample points in A. This sum is called the probability of A and is denoted by P of A, which is like this. Now, from this we can easily say one thing, that probability of the whole sample space is always 1. So, we can write in this way that summation of P of x, x belonging to S is equal to 1. So, let us consider one example in this context. For the experiment of rolling a die, the sample space consists of 6 samples. If we suppose that probability of occurrence of any outcome is equal, then the probability of getting an odd number is equal to 3 by 6, that is half, because there are only 6 possibilities in the sample space. So, sample space contains 6 sample points. So, that is why the denominator is 6 and the numerator is 3, because the number of favorable cases will be 1, 3 and 5, because these are the odd numbers available in a die. So, that is why it will be 3 by 6, which is half. Now, let us consider another example. It is very important example. Let us suppose that a die is loaded so that the numbers 2 through 6 are equally likely to appear. But that one is 3 times as likely as any other to appear. Now, to model this situation, we should have probability of 2 equal to probability of 3 equal to probability of 4 equal to probability of 5 equal to probability of 6. And another condition is probability of 1 is equal to 3 into probability of 2. Since we know that summation P of x, x belonging to S, is equal to 1, that is why probability of 1 plus probability of 2 plus probability of 3 plus probability of 4 plus probability of 5 plus probability of 6 will be equal to 1. So, we can write that 3 into probability of 2 plus 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 probability of 2. So, that will be equal to 1. So, from this we can find the value of probability of 2, which is equal to 1 by 8. So, we can find probability of 1, that is 3 by 8. So, now if we have to find the probability of an odd number, it will be probability of 1 plus probability of 3 plus probability of 5, and that will be 3 by 8 plus 1 by 8 plus 1 by 8, which is 5 by 8. Another very known and important problem we can discuss, that is known as birthday problem. So, the problem is like this: find the probability that among n persons at least 2 people have birthdays on the same month and date, but not necessarily in the same year. Assume that all months and dates are equally likely, and ignore February 29 birthdays. So, let E denotes the event that at least 2 persons have the same birthday. So, the event E prime will be the event that no 2 persons have the same birthday. Now it is easier to compute probability of E prime than probability of E. And we can find probability of E from the fact that probability of E plus probability of E prime is equal to 1. Since all months and dates are equally likely and we are ignoring February 29 birthday, the size of the sample space will be 365 to the power n, because there are n persons. So that is why the sample space will contain 365 to the power n sample points. The first person's birthday can occur on any one of 365 days. If no two persons have the same birthday, the second person's birthday can occur on any day except the day of the first person's birthday. Therefore, the second person's birthday can occur on any one of remaining 364 days. So, first person's birthday can occur in 365 days. Then second person's birthday can occur on any one of remaining 364 days. Then similarly, if we proceed, third person's birthday can occur in 363 ways, or we can say it can occur on any one of the remaining 363 days. In this way, if we proceed, we can say that the size of the event E prime, that no two persons have the same birthday. No two persons have the same birthday. The size of this event will be 365 into 364 into 363. In this way, the last one will be 365 minus n plus 1, because there are n persons. Therefore, the probability that at least two persons have birthdays on the same month and date is 1 minus $365 into 364 into 363 in this way, 365 minus n plus 1 divided by 365 to the power n. Now, if we consider n equal to 22, so that means if there are 22 persons, then this probability will be, then the probability is 0.475695. If n is equal to 23, then the probability is 0.507297. Thus, if n is greater than equal to 23, the probability is greater than half, that at least 2 persons have birthdays on the same month and date. So, from this problem, this is our conclusion. So, that is like this: if there are more than or equal to 23 persons, the probability is greater than half that at least 2 persons have birthdays on the same month and date. Here is another example. This is also very interesting example. 10 men went to a party and checked their hats when they arrived. The hats were randomly returned to them when they departed. We want to know the probability that no man gets his own hat back. For the experiment of returning the hats to the men, the sample space consists of 10 factorial samples corresponding to the 10 factorial possible permutations of the hats. let us assume that each permutation occurs with equal probability, that is 1 by 10 factorial. Consequently, the probability that no man receives his own hat is equal to 1 by 10 factorial times the number of permutation in which no man receives his own hat. Let AI event, this is an event, let AI denotes the set of samples in which the ith man receives his own hat. So, the number of favorable cases that at least one person will get his own hat can be written as this cardinality of A1 union A2 union A3 dot dot union A10. So, now how can we find this cardinality? So, that is the next challenge. So, let us consider, so we have A1 union A2 A10. So, this can be written as summation I equal to 1 to 10 cardinality of AI minus summation I less than j of the cardinality AI intersection AJ plus summation I less than j less than k cardinality AI intersection AJ intersection AK minus so on. So, it will continue in this way. The last entry will be minus 1 to the power 10 minus 1. So, that will be 9 cardinality of A1 intersection A2 intersection so on intersection A10. So, this is coming by inclusion exclusion principle, which has already been covered in set theory. So, we have like this. Now, what is this summation of the cardinality AI? So, that means here we have to find the number of ways that one person will get the hat correctly. So, that means number of ways one person will get his own hat. So, let us come to now this slide. Here summation I equal to 1 to 10 cardinality of AI. The number of ways that one person will get his own hat is 10 choose 1. So, for each of these cases, the other arrangements can occur in 9 factorial ways. So, that is why the resulting number of ways will be 10 choose 1 into 9 factorial. In this way, the next one is that 2 persons will get their own hat, and that number is 10 choose 2. And for each of these ways, the other arrangements can occur in 8 factorial ways. So, the resulting number of ways will be 10 choose 2 into 8 factorial ways. So, in this way, the last one will be 10 choose 10 0 into 0 factorial. So, there 10 people will get their own hat in 10 choose 10 ways. So, in this way, if we find the cardinality of A1, A2 and so on union A10, then we can find the probability that no man receives his own hat in this way. So, it will be 1 by 10 factorial into 10 factorial minus the cardinality of A1, A2 up to union A10. So, that cardinality, which is nothing but 10 choose 1 into 9 factorial minus 10 choose 2 into 8 factorial up to minus 10 choose 10 into 0 factorial. So, the term inside the bracket is coming in this way, that number of all possible cases which we have already noted down, that is 10 factorial. So, 10 factorial minus that cardinality of A1, A2 union A10 will give this term inside this bracket, which will give the number of ways that no man receives his own hat, and we are dividing it by 10 factorial to get the probability of this event. So, it will be 1 minus 1 by 1 factorial plus 2 by 2 factorial minus 3 by 3 factorial and so on up to plus 10 by 10 factorial. So, if we calculate this, we will get the value 0.36788. Now, there are three axioms of probability: 0 less than equal to probability of A less than equal to 1 for any event A. This is the first axiom. Second axiom is probability of a sample space is 1, which we have already mentioned. Now, if A1, A2 to A3, A1, A2, A3 and so on is a sequence of mutually exclusive events, then probability of A1 union A2 union A3 union like this will be equal to probability of A1 plus probability of A2 plus probability of A3 plus so on. So, this is sum of the probabilities of these events, individual probabilities of these events. So, the first axiom is obvious, second axiom is also obvious, we have already mentioned. Now, what about the third one? Before going to this axiom, let us prove one result here. Let E1 and E2 be events, then probability of E1 union E2 is equal to probability of E1 plus probability of E2 minus probability of E1 intersection E2. The proof is like this. Let E1 is equal to x1 x2 to xi, E2 is equal to y1 y2 to yj. Then E1 intersection E2 is considered as z1 z2 to zk. So, let us describe this by Venn diagram. So, it will be like this. So, this is E1 event, this is E2 and this one is E1 intersection E2. So, E1 is having the members x1, x2, x3, x4, x5, x6, x7 and E2 is having 6 members y1, y2, y3, y4, y5 and y6, and E1 intersection E2 will be like this. It is having two members Z1 and Z2, and Z1 is same as x2, which is same as y4. So, x2 and y4 are same. So, those are denoted as Z1, and x5 and y5 are same. So, these two are denoted by Z2. So, E1 intersection E2 will contain two members Z1 and Z2. And assume that each set element is listed exactly one time per set. Then in the list x1, x2, xi, y1, y2 to yj, z1, z2 to zk, so in this list x1, x2 to xi, y1, y2 to yj, z1, z2 to zk occurs twice. So, from this it follows that probability of E1 union E2 will be equal to summation probability of xt t equal to 1 to I plus summation probability of yt t equal to 1 to j minus summation probability of zt t equal to 1 to k, and this is equivalent to probability of E1 plus probability of E2 minus probability of E1 intersection E2. Because we have already seen that Z1, Z2 to Zk occurs twice if we list x1, x2 to xi, y1, y2 to yj. So, that is why one time we are subtracting it from this list. So, we will get probability of E1 union E2. So, once it is proved, then we can consider the third axiom of probability, which says that probability of A union B will be probability of A plus probability of B, when A and B are mutually exclusive events. So, this will come from the previous result, that is we know that probability of A union B is probability of A plus probability of B minus probability of A intersection B. So, this result is in general. Now, if A and B are mutually exclusive, we know A intersection B will be equal to phi, and that is why probability of A union B will be simply probability of A plus probability of B, because probability of A intersection B will become 0. In this way, if there are 3 mutually exclusive events A, B, C, then from the inclusion exclusion principle we know that probability of A union B union C is probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of A intersection C plus probability of A intersection B intersection C. So, since A, B, C are mutually exclusive events, all these probabilities will be equal to 0, and that is why we will get A union B union C equal to probability of A plus probability of B plus probability of C. So, let us consider the third axiom here. It says that there are mutually exclusive events A1, A2, A3. So, infinite number of mutually exclusive events. So, probability of A1 union A2 union A3 union so it will continue. So, this will be the sum of the probabilities, individual probabilities of A1, A2, A3 and so on. Because the same reason, the probability of the event A1 intersection A2, A1 intersection A3 will all vanish, and that is why we will get only the sum of these probabilities. So, let us discuss now the conditional probability. The probability that event A occurs given that event B has already occurred is defined as the conditional probability of event A given the occurrence of event B, which is denoted by probability of A given B. So, this. For example, suppose a die is thrown, then if it is asked to find the probability that 4 will appear given that even number has occurred. So, the probability that 4 appeared given that even number appeared will be equal to 1 by 3, because even numbers, there are only 3 even numbers 2, 4, 6. So, among this the probability that 4 will occur with probability. So, probability that 4 will occur will be 1 by 3. So, in general, let P subscripts B of xi denote the probability associated with sample xi given that event B has occurred. Now, for xi does not belong to B, probability subscripts B of xi will be equal to 0. However, for the samples in event B, their relative frequencies of occurrence remain the same while the sum of their probabilities should equal to 1, that is summation of probability subscripts b of xi such that this xi belongs to b, that will be equal to 1. Consequently, we need to scale the probability to each of these samples up from probability of xi to probability of xi divided by probability of b. Thus, we have probability of xi is equal to 0 when xi does not belong to b, and probability of xi divided by probability of b when xi belongs to b. It follows that probability of a given b is equal to summation pb of xi, and that is equal to summation xi belonging to a intersection b probability of xi divided by probability of b. Now, 1 by probability of b we can take out of this summation. So, we will get 1 by probability of b into summation xi belongs to a intersection b of probability of xi, and that is equal to probability of a intersection b divided by probability of b. So, we are getting the definition of conditional probability in this way. So, probability of a given b is probability of a intersection b divided by probability of b. So, let us take one example in this context. 3 dice were rolled. Given that no two faces were the same, what is the probability that there was an S? Let A denote the event that there was an S and B the event that no two faces were the same. Now, probability of B will be 6p3, that is nothing but 6 into 5 into 4. Why is it this? The first one, so what is B actually? B the event that no two faces were the same. So, the first dice can give 6 outcomes. So, there are 6 possibilities. Now, one outcome has already occurred from the first dice, and that can occur in 6 ways. So, once that occurs, the second dice will give 5 possible outcomes, because the number which has already occurred in the first dice, that is discarded from the list. So, that is why it will be 6 into 5. Then once the first one and second one have occurred, the third dice will give the outcomes in 4 possible ways, because the first outcome and second outcome we have to discard from the list. So, there will be 4 outcomes remain. So, that is why we will have total number of outcomes 6 into 5 into 4, which is 6 p3, and all possible cases. What is the number of all possible cases? It will be 6 cube. Okay. So, 3 dice are there. So, that is why 6 into 6 into 6, 6 cube. Next, we have to find the probability that A intersection B, that is both A and B will occur. A is the event that there was an S, and B the event that no two faces were the same. Now, if one is already fixed, one is an S, so that is why there will be only 5 possibilities, because A and B both will occur. So, that is why that outcome is gone from 2 dices. So, that is why it will be 5 P2, 3 into 5 P2. So, 3 dice are there. So, for each of this case we will have 5 P2 possibilities. So, that will be, so total number of cases will come 3 into 5 P2, and the denominator is 6 cube, because this is the number of all possible cases. So, probability of A intersection B will become 3 into 5 P2. Thus, probability of A given B will become 3 into 5 P2 divided by 6 P3. If we calculate this, we will get half. So, the conditional probability will be half. So, this is the end of this lecture. Thank you.